Good morning,
Okay.
everybody. Welcome to the High Energy Density Science Center seminar series. Today I'm pleased to welcome Dr. Sebastian Merkel, who is an expert on high pressure mineral physics. He is a professor at the Université in France and the president for mineral and rock physics at the American Geophysical Union. Dr. Merkel was originally scheduled to give the seminar 1 year ago tomorrow, but we had to cancel due to the pandemic. And his was the first seminar to be affected, and I am happy to be able to invite him back in this virtual forum and hope it will be less than another year that we will be able to have him and other speakers here in person. Dr. Mikhail moved to 2006 and was promoted to a professor in 2010. Before moving to Lille, he was a postdoctoral fellow at UC Berkeley and the University of Tokyo in Japan. He did his PhD between the Carnegie Institute in Washington, D.C. and the École Normale Supérieure de Lyon in France. His research focuses on understanding the dynamics and formation of the deeper portions of the Earth. He performs experiments under the pressure and temperatures of the Earth's interior to study first structures and polycrystals, their mechanical behavior, and their relation to phase transformations and wave propagation through these complex microstructures. This work aims at understanding the dynamics and formation of the Earth's mantle and inner core. So I'd like to inform everybody that this talk will be recorded. Comfortable with that, please log off. And also it's open to external researchers, and it's of course an unclassified talk. So please be aware. But otherwise, I'm looking forward to listening to it, and please take it away, Dr. McHale.
Okay, well, thank you for the introduction. And in fact, yes, I was supposed to give a talk last year, almost a year ago. I think maybe even exactly a year ago. And I cancel
Yeah,
everything.
a year ago tomorrow.
A year ago tomorrow, yeah. And then I flew out of the US. I was going to finish the
Yeah.
talk. I was escaping, going home. So yeah, so thank you for the invitation to give this talk a year later. So good morning, good evening here, and so I'll be speaking about what we do here under high pressure to study microstructures of materials. So I hope everything will go well. If anything, the slides or the sound try to flag me down, I hope I will see it. And so, what are materials microstructures? Well, materials microstructures, they are the arrangements of elements inside a material, distribution of phases, grain sizes, grain orientations, grain boundaries, and etc. And they are relevant for multiple material properties, and in particular for the rheology of materials, for mechanical properties, strength, wave propagation, elastic anisotropy, and many more. And I put a few examples of what microstructures look like. Like this is what microstructures look like in a polycrystalline olivine, a mineral for the deepers, or in metals as well. It's a very common field of study. Now, why do I, as a geophysicist, care about microstructures? Is one application is, for instance, we have an isotropy of propagation of seismic waves. Seismic wave in the inner core of the Earth travel faster if they go north to south than if they go east to west. And where is this coming from? Can it tell us something about what's happening inside the inner core, or about its history, how it was formed, how old is it? Because it's one of the few tools we have to observe such deep regions inside the Earth. This is why it's so important to geophysicists. Now, if you look at the microscopic scale, why do we have an isotropy of propagation of waves? It's because minerals are anisotropic in terms of elasticity. You'll get anisotropy in the wave propagation depending on their elastic properties, and most minerals are anisotropic. But if they are randomly aligned in a polycrystal, then you won't get any form of anisotropy. On the other hand, if you have a texture, if you have lattice preferred orientation, then you'll get anisotropy again. And this depends, the anisotropy you get depends on the single crystal properties, on the elastic constants, but also on the microstructures. hence the importance of looking at microstructures for the deep Earth. And these microstructures can arise from deformation, phase transformations, multiple processes. As an illustration, for instance, a few years ago, we did a model of inner core anisotropy. Like we tried to model a formation of the inner core. So we built a geodynamical model of the inner core growing over time, over 1 billion years, and calculated the strains inside the inner core. And then, we actually applied mechanical properties and microstructure development based on what we know about the deformation of iron under those conditions, and then try to then build a model of the core as it is today. And we propagated model through this virtual inner core that we had built to try to simulate, to do a forward model of the observations of anisotropy with the idea of comparing it to the true data. And the key questions in terms of high pressure physics or mineral physics is what is driving the evolution of microstructures? What is the effect of plastic flow? What is the effect of phase transformations? And how does that depend on the material and pressure and temperature conditions? So I'm geophysicist mostly, so the type of pressure and temperatures I will be interested in are those of the Earth's mantle and core. So at the core mantle boundary, we are 2,900 kilometers deep, and we're talking of pressures of 135 GPa, 3,000 Kelvin. At the center of the Earth, we are at the depth of 6,300 kilometers, nearly 6,400, and pressures are on the order of 360 gigapascals, temperatures on the order of 6,000 Kelvin. So this is the type of pressure temperature range that will be relevant for deep Earth geophysics. I study that experimentally. I guess a lot of people on the call here probably know what is a high pressure experiment in the laser heated diamond anvil cell. So I do a lot of my work in the laser heated diamond anvil cell. In the laser heated diamond anvil cell, so where we can reach the pressures of the center of the Earth by compressing samples between two gem diamonds. Just the only problem is that samples are small, but apart from that we can. And then by focusing infrared lasers, we can actually reach temperature in kelvins. I also perform experiments using multi-anvil presses, large volume presses. This is an example of the large volume press at ESRF, the European synchrotron at ID6, where the pressures we can reach are not as high, but the advantages of using a multi-anvil press is we can use much bigger samples. This is a sample assembly which goes inside the press. The sample are mini. We can also control the pressure, the temperature, but also deformation much better than in the diamond anvil cell. But then the pressures you can get with that press are maybe on the order maybe 20 GPa if you push it hard. And I've also performed some laser-driven compression experiments. I'm giving a talk at Livermore here, so I guess most of you know about that, where we can reach very high pressures, temperatures by focusing high-power lasers to polymer on the back of a sample that will, then that will generate a shock wave or various type of compressions inside the sample, and then reach pressures, temperatures which are actually well above those of the Earth's interior. Something I like to focus when I give presentations in general is how important it is to couple those facilities, those techniques with large-scale facilities. Like for static experiments, we perform experiments at synchrotrons, at the ESRF, the European synchrotron, for instance, the Soleil synchrotron outside Paris. We can also use free electron lasers, and these dedicated beamlines on large-scale facilities are really key to this research because they offer intense and very high power X-ray sources, and they are very well suited for high pressure, high temperature experiments with dedicated setup which are in place and aligned. And this is what allows us to do actually a lot of the good science in the field of high pressure research. It's not the only way, but it is a very important way, and I like to focus on that because large-scale facilities are expensive, but it's where the science gets done. And we do measurements using X-ray diffraction, radiography, tomography, EXAFs, spectroscopies, many types of science and measurements. So now that I've introduced the topic, I told you I was going to speak about microstructures, which is what we focus on, and I was going to give you two examples of the work we do here in Lille and with collaborations, actually you'll see later. And the first will be on static experiments, where I'll be looking at microstructures induced by phase transformations. So I'll look at deep earth oxides and how the transformations can affect grain orientation, grain sizes, and the geophysical implications. And then I thought, since we have results, it would be interesting to speak to this audience about stress and texture in shock compressed iron, which we've done experiments on at SLAC a few years ago. So transformation microstructures, it's a project I I've been working on for several years, and at the moment we have a large grant between France and Germany with several PhD students to work on this. And so the idea is to look at transformations in oxides and what is the effect on grain size, grain orientations, and how relevant is it for the Earth's mantle. For instance, we have this transition between perovskite and post-perovskite. So the perovskite is a dominant mineral in the lower mantle. The post-perovskite is, we think, dominant in the double prime layer just above the core mantle boundary. And it's one of the most important phase transformations when you look at the Earth's mantle. And it was discovered in 2004 and has been driving research since, so for the last 15 years. And this is what people have suggested on how this transformation can be happening. The first simulations of Taku Tsuchiya, for instance, in 2004. So he suggests like there's a distortion of the perovskite lattice that will lead into the post-perovskite phase. And then Artem Oganov made models where he was, and he had this complex metadynamics model where stacking folds will be moving through the material and allow you to go from this perovskite phase to this post-perovskite phase. But then later there were experiments on analogs, NiO3, where they've been looking at electron microscopy and found orientation relationships between perovskite and post-perovskite. Now, if you look in details about these mechanisms that have been suggested, they're actually different in the way the crystals will be oriented relative to each other. With the first mechanism, you get a 45 degrees rotation around the C-axis to go from a perovskite to a post-perovskite. With the second mechanism, it's pretty much random. It's a random rotation around the C-axis. With the model of David Dobson in 2013, it's a 16.7 rotation around the C-axis. So those are different, and actually, do they even apply in polycrystals is one of the questions. Now, why do we care? It's important in geosciences, it's important in geophysics because we think it will be relevant for the D double prime layer. Whoops, let me go back. Where imagine if you have a slab that's arriving at the core mantle boundary, you'll have this transformation between perovskite and post-perovskite. And the question is, are you keeping a memory of the microstructures? Are you keeping a memory of the texture when you go to the post-perovskite phase? And what does that do on the seismic measurements that we do down there? Or are we resetting everything? Do we get a full reset? Is the material after the perovskite to post-perovskite transformation just clean of the history of what was happening before? So if I look at the details of these mechanisms of David Dobson, for instance, this is how he suggests you make a post-perovskite out of a perovskite. So this is a perovskite in green and post-perovskite in red, and so you can, out of each parent orientation of perovskite, you can have two daughter orientations of post-perovskite, and each have a 16.75 degrees rotation relative to perovskite. And now, does that does it go between those two variants, those two daughter phases? Which one is going to grow? Are you going to have one of the two or the two of them? This type of questions we want to answer. To approach this problem, we use multigrain crystallography. Multigrain crystallography is kind of a new technique, and the idea is to step scan a diamond anvil cell in front of the X-ray beam. So instead of collecting data with your diamond anvil cells, the X-ray beam, and just shooting X-ray diffraction data, you step scanning like you will do it with a single crystal, but you save every images. And we typically rotate over 45 degrees and collect data every 0.5 degrees. That gives you 90 diffraction patterns per PT point. And then you look at the spots. All those spots you get because your samples has grains and it's very spotty. It's common in diamond cell experiment that the diffraction images are spotty. But here we actually extract them one by one. And so we get a database of spots we measure as a function of angles. So this eta angle, azimuthal angle on the detector, to theta diffraction angle, and the omega rotation at which we saw the diffraction spots. To get to that type of information, the idea, the way you do it is you have these images you acquired at every step in the rotation. And you can, for each pixel on the detector, you can calculate the median value of the diffraction intensity that you measured. And you get this median image, which the median image actually, this has the effect of keeping the background, the powder, but the spots are removed from that image. And if you subtract the median image from the diffraction image, then the spots show up very easily. You completely get rid of the diamond cell background, the diamond diffusion and the powder signal and whatever is on the way is completely gone. You only keep the spots, the bigger grains in the sample. And then it's just a high pass filter to locate all the spots and those peaks. Based on those images, you can actually even get a first set of information because the average of all of those diffraction images include the signal from everything, large grains, background, small grains, whereas the median image includes background, small grains, but not the large grains. And so this tells you an idea it tells you something about your sample. And if you do an integration of that image and plot the intensity versus 2 theta, the ratio between the two sets of intensities you will get tells you how much of your sample is in the form of grains and how much of your sample is in the form of a fine powder, which you can't see. Now, how do we do that? When typical capabilities, we are working with about 10,000 diffraction spots per pressure, and then we do random walks through orientation space to locate the grain. So we do typically a million trials, and that allows us to index on the order of 500 grains, sometimes less, sometimes more at each pressure. And then for each grain, we get ideas on their orientation, their cell parameters, their relative volume. We've already published quite a few papers on this. The references are here, but also since we have these grants in which we are training many students, we actually, we wrote a wiki for those students as we were training them, and so it's now available online, and it tells us how we do this type of data analysis if you are interested. I also wanted to say that there is a project of having a working group at the International Union of Crystallography, which will be called Diffraction Microstructure Imaging, as a project will be sent pretty soon actually. And so we hope this will be part of the International Union of Crystallography soon. Not only for high pressure, for many fields in material science. So I'm going to show some illustrations with going from a perovskite to a post-perovskite phase. I'm not going to look at the true phase in the deep mantle because it's at the moment outside our reach for this type of experiments. Here we worked on this cobalt analog because the pressure and temperatures you can reach with resistively heated diamond anvil cell. And so what we did is we heated a sample to 900 Kelvin, compressed it to in the perovskite field, converted it to post-perovskite, and then we look at the grains in perovskite before transformation, then look at the grains in post-perovskite after transformation. And then we're going to go back from post-perovskite to perovskite. So what I'm going to show now are the statistics of grain orientations that we measure in perovskite at before the transformation, and then in post-perovskite after the transformation, as we increase pressure from 14 GPa to 17 GPa. So when we look at perovskite, we were able to index 1,000 grains, 1,100 grains. And what is plotted below, it's the projections of the grain orientations with the diamond cell direction is on the side here. If you don't know how to read the pole figures, it's okay. What matters is each point here on this figure is a grain, and where it is located on the figure tells you about the grain orientation. And so we are following the orientation of 1,000 grains inside the sample. Now, as we go to post-perovskite, we can perform the same exercise. And so we are 3 GPa higher, and we perform an indexing of our diffraction data using post-perovskite. And now you can see that we have now 800 grains, and we have their orientation distribution. For each grain, we know where they are. I mean, we know their space in where they are in orientation space. And when we started the project, I wanted to be able to say, oh, one grain here is this guy in perovskite is becoming this guy over here in post-perovskite. And as a matter of fact, it doesn't work. We don't have enough orientation resolution for that. But we can look at it, features. So for instance, the first thing we can see when we compare those two distributions is that the number of grains is multiplied by a factor of 2.5. When we look at the orientations of O1 planes, well, they are pretty much matching between O1 of perovskite and O1 of post-perovskite. And if you remember the mechanism that were suggested, it was a rotation around 001, so it makes sense, and it's compatible with those mechanisms. Now, if we look more carefully, it's not as easy to see, but the orientations of 100 in perovskite are not so far from the orientations of 010 in post-perovskite. And that matches what David Dobson suggested, not the other two. If you had the Tsuchiya model, it would rotate by 45 degrees. If you had the Oganov model, it'll be random. And so it actually goes in favor of the Dobson model. You can go a little bit further than that, you can actually simulate it. So you know the orientation relationship. So you can say for each grain of perovskite, I know this perovskite is going to have 2 daughters, and these daughters are going to be with this orientation. And so if you do that, perform this simulation, this is a simulated pattern. So this is a simulated grain orientation, and over here is a measured grain orientation in the experiment. And there's a pretty good match. I mean, it's not perfect, but some features are the same. And if you look more carefully, we have 2,200 grains in the simulation. We have 2,800 grains in the experiment. And so those grains have been coming from somewhere. And I think they've been nucleating randomly from the powders that's floating around the sample. And if you add 641 grains, which are the missing grains, if you do just the counting, you add them randomly into your simulation. This is the simulation. This is the data. So there is a very, very good match between the data and the simulation on the mechanism of and so it's very consistent with the mechanism of transformation between perovskite and post-perovskite that was suggested by David Dobson. You can also extract grain size distributions based on these measurements. I won't go into the detail, actually, just so you can do it. Now, what I want to see is what happens if you go back, if you go from post-perovskite to perovskite. Is it the same mechanism or is it different? So now we're going to go from a post-perovskite at 18 GPa, and we're going to lower the pressure to 13 GPa. And this is the results. You go from 1,000 grains of post-perovskite at 18 GPa. And as you go down, you go to 300 grains, 300 orientations actually in perovskite. And if you look at those 300 orientations in perovskite, they actually are very concentrated around one specific orientation for 001 and two orientations for 010 and 100. So, and if you look in this board figure and look at the rotations to go from one to the other, you realize that to go from here to there, it's an 86 degrees rotation around the z-axis, which actually happens to be a twinning mode in perovskite. So what I think we're forming when we go back to perovskite, we're not forming many grains of perovskite, we're actually forming one big grains with many twin domains. I don't know why, but it's very different from when you go up in pressure. When you go up, it's actually a martensitic transformation with orientation relationships. When you go down, it's a diffusive transformation with complete reconstruction of the microstructure. The take-home messages, from that experiment is that if you go from perovskite to post-perovskite in NSEO3, well, you get an Dobson-like mechanism with orientation memory. It's a Martensitic-like transformation with a division of grain sizes by 2. And then if you go back to perovskite from post-perovskite in this compound NaCO3, the grain size gets multiplied by a factor of 10. And you lose the orientation memory, so you don't have any memory of the orientation before. In the figure here, the crystals of perovskite that we are growing don't have any specific orientation relative to the experiment, orientation relative to the starting material. It's just one orientation that just started the transformation and then took over, I believe. Now, if I so what are the consequences of that? Like, if you are talking in terms of geosciences, in terms of geosciences, well, you know, like you imagine you have a dull welding slab that goes down in the lower mantle. You'll have deformation of your perovskite polycrystals through dislocation glide, dislocation climb, diffusion, whatever. You'll be building a microstructure in perovskite as your material is going down in the Earth's mantle. As you make post-perovskite, you'll get a transformation to post-perovskite, and you will keep a memory of the microstructure in perovskite. It will be changed, but there'll be a memory, and the grain by 2. Then, as your material is going down along the core mantle boundary, you will have changes in grain orientation through plastic deformation, through motion of dislocations or whatever, maybe grain growth, and develop a new type of anisotropy, a new type of texture, new type of microstructures. Then, when you'll be reaching a region of high temperature where you transform back to perovskite, you will lose the memory of all of that, and you'll and clean material. They'll be fresh, you'll be clean, and actually, apparently, from the experiment, you even get a grain size multiplication by a factor, which is quite significant. Then, perovskite will be driven up in the Earth's mantle and again deformed through dislocation, climb, glide, or whatever mechanism it wants to deform and developing its microstructures. So this is one application. But as you saw, we were working, so it's a very interesting results, but we were limited in the pressure and temperature range. We couldn't work on the true perovskite, post-perovskite that we wanted to, that would be relevant, that will be the one you'll find in the Earth's mantle. For that, you need laser heating, and you need to be able to rotate your diamond and bell cell in front of the X-ray beam while collecting X-ray diffraction. And it's actually possible now. I mean, it was before the ESRF went for repairs, just installed it at ID27. They just installed a system like that, and we're lucky enough to use it. So this is a drawing, this is a picture of the system. So the X-rays here are in green. The detector is to the back, the beam is coming from the front, and the sample diamond anvil cell will be sitting here. And this is a laser heating system that is shown in red. And it's being held by two huge arms, which you can't see on the picture, but below there is a rotation stage, and you can actually rotate that whole thing in front of the X-rays. So I had a movie, but it wasn't playing very well, so I took screenshots. And so this is our diamond anvil cell on this rotating laser heating setup at ESRF that we measured just before they closed 2 years ago. And so the laser, this is a laser heating system and the diamond anvil cell. This is our 2D detector, and the beam is coming from the back. And then we can actually rotate the diamond cell while laser heating. So we can actually collect this type of step scan data while laser heating and while maintaining the sample at a relatively constant temperature. So as the first applications, we looked at what's happening in olivine and wadsleyite, which are relevant for the Earth's upper mantle and transition zone. And so here, what we are looking at, it's just a sample of the results. It's the ongoing work of Estelle Ledoux. She's working on, she's finishing up right now. Where we look at olivine at 1700 Kelvin, 21 GPa, and then we increase pressure on the sample and transform to wadsleyite while keeping laser heating. Pressure goes down due to the phase transformation, and then we keep increasing pressure to 18 GPa, 19 GPa, and all along the way we keep the sample at 1700 Kelvin, and we at each step in pressure we stop the pressure increase, collect multi-grain diffraction, and then go on and go again. And so the difference between the previous type of experiment and this one is the temperature. We actually can work at several thousands of degrees and stay there for hours. We've actually been able to do such experiments over like 20 hours or so. And so then we can follow grain orientations in olivine and wadsleyite. What's plotted here is inverse pole figure, and again the dots tell you something about grain orientations. So here I won't tell you the whole story to walk you through the whole story, but in this case the transformation is reconstructive. We don't have orientation memory between olivine and wadsleyite, and then as we compress wadsleyite, we see the development of lattice preferred orientation, development of texture, which we can then correlate to slip systems and deformation. So this is what I had prepared for microstructures induced by phase transformations, and then so I will switch to a slightly different topic, which I thought would be of interest to you, to this audience in Livermore, where we look at texture and stress in shock compress HCP iron. So it's a completely different project. Work we've done with Ariana Gleason in Stanford and SLAC, and many people in Stanford, Los Alamos, and UC Berkeley. And actually, for the short story, this is why I was in Stanford last year, just before the lockdown. I was working on this data. So we are using laser-driven compression at the SLAC beamline. The idea is we have an iron sample. We drive the lasers of the SLAC beamline, the MEC beamline at SLAC to reach high pressure, high temperature in HCP iron. So in our case, we'll just be following the Hugonia. We didn't do anything complicated like go on to isotopes or anything like that. And so we did the experiment at SLAC on the MEC beamline. We had the sample holders and with many targets, so we could repeat the experiment. What was the thing that was different in this experiment was the layout of the detectors. The detectors were laid out in a way that we could get maximum coverage of orientation for texture and stress analysis. So Cindy Bolmer actually and Ariana had thought very hard on how to place all of those small detectors and large detectors around the sample, so we could get an idea of stress and texture, and then the FEL beam was launched at 65 degrees relative to the shock direction to allow something that looks like what we call radial diffraction, for instance, in diamond anvil cell data. And this is why I was called in, is for my ability to process this type of data. So we have 4 pressure and temperature ranges in this set of experiments. I will be mostly speaking of this one here, where we have results at nearly 2 megabars and 4,000 Kelvin. And then we also have results in the lower pressure range between 20 and 55 GPa. The idea is this is a type of measurement we do in static experiment to look at stress and textures in polycrystals. These are measurements in a large volume press on zinc. You collect 2D X-ray diffraction and with a specific geometry where you can actually see the effect of stress. And as you compress the material, if you put stress, the Debye rings will be distorted and will become like ellipses. And as your grains rotate, you'll develop textures, lattice preferred orientation, and that will show up as variations of diffraction intensity. It's not easy to see on such a figure, but if you look at the integration as a function of azimuthal angles, is delta or eta angle, depending on convention, then it's easier to see. And this is the same diffraction pattern plotted with 2 theta in horizontal, the azimuthal angle here. So you are turning around the diffraction rings when you move up. Sorry, I was pointing on the wrong screen. When you move up on the vertical direction, you see variation of diffraction intensities with orientation, that is texture. You see variations of peak positions with orientation, which is strain, and from which you can try to invert stresses. So it's very commonly used in static experiments. The idea is to do that on the shock. This is the type of X-ray diffraction data we managed to collect and reconstruct based on at the MEC beamline. So this is an example. It's HCP iron at 193 GPa for 4,000 Kelvin, based on the unit cell volume. This on top is on the bottom is the data. On top is the reconstruction. And you can see diffractions from the ambient pressure BCC, which has not been reached by the shock yet, and then of the high pressure HCP phase. The data looks very noisy and very, the coverage is not complete, far from it. But we're lucky that we can assume that there is some form of axial symmetry around the shock direction. And which allows us to make a lot of assumptions on how the stress and the texture should look like. And then HCP materials have a lot of redundancy, so you don't need so many peaks to get some data. And then you can get a fit of unit cell parameters, lattice strains, which is the effect of stress, the way peaks move with orientation, this is stress, and the variation of peak intensities with orientation, it's texture. So here are the results for HCP iron. So on the left, you have a simulation with the pressure as a function of time. The time is vertical in this figure, and the sample of iron is here. Color is pressure up to 2 megabar. I put time equals 0 when we see HCP. And this is the X-ray diffraction measurement evaluation of stress and texture. So here we're plotting stress here as a function of time. The dots are the points where we actually measured X-ray diffraction data, and the blue is just a guide. And then texture that we measure in the sample. I will focus on the texture a little bit. So 0.59 seconds after transformation, nanoseconds, sorry, after transformation, we get a texture with a maximum at 2 minus 10. And then as you move, as the shock front is moving through the sample, the texture switches to 30 degrees away from 001. I have drawings here. So if you're not very comfortable with textures, this is what happens. When you form HCP ion from BCC in the shock, you get a texture, grain orientations with the C-axis are perpendicular to the shock direction. And then as the shock is moving through the sample, the grains are rotating. And they rotate to an orientation where their C-axis are rotated 30 degrees away from the compression direction from the shock. Now, how does that? What is the reason for that? So we can try to do modeling of texture evolution. It's something we do very commonly for HCP metals. So this is the VPSC simulation, so viscoplastic self-consistent, where I can force a deformation mechanism to take over the plasticity and grain orientations. And this is the result. So this is the type of textures we measured in the experiment as a function of time, as the shock is moving through the material. And this is the experiment, the simulation results. So here is the starting texture in the simulation is the experimental texture after transformation. If I run a simulation saying that texture is due to basal slip, this is what I get. If I run a simulation saying dominant prismatic slip is dominating grain orientation, this is what I get. If I say it's pyramidal C plus A, this is what I get. And if I actually assume that the dominant deformation mechanism is twinning, this specific type of twinning, which is common in UCP metal, 1 or minus 1, 2, then I get something which actually is really close to what we see in the experiment. So what's happening when we go from a texture at 2 minus 10 to this one, 30 degrees away from compression, from C, is the grains are twinning. The grains are twinning under the effect of shock, under the effect of plasticity. You get grain orientation through twinning. Then later in the shock, we get an increase again of the starting texture, and it's just due to the shocks that's moving through the sample. And there's new grains of HCP being generated, and they are generating with a starting texture, and then they slowly twin. Now, if I focus on the stress curve, so I've zoomed in on the stress curve, which I showed you earlier. This is the time in nanoseconds in horizontal stress in HCP iron that we deduce from X-ray diffraction, and this is how it looks like. And we actually were quite puzzled about that. That's not what I expected. And now this is how I interpret it. So this is my interpretation. It's a bit busy, sorry. So I think what's happening is as the shock is coming into the sample, you get a big increase of stress, of elastic stresses, until you get enough defects to be generated to activate plastic flow, plastic deformation. And then so you get a transition from elastic to plastic behavior at the yield strengths, and then plastic relaxation through 1O minus 1O, minus 1,2 twinning. And then as you activate plasticity, the polycrystal can relax stresses, and so it goes down. And it goes down to something at the long term, what I call the long-term flow stress, which is much lower than the peak stress at the onset of plasticity. And our values of stress are not so high. The peak stress we didn't measure, unfortunately. We didn't know this was going to happen. But it's probably quite high. But then actually it's quite surprising that we get very low stress values on the order of 5 GPa 2 to 5 GPa later in the compression. This was modeled. I mean, there are predictions that the stress curve should behave that way. And I think I saw Nathan Barton's name on the list of people, and he has papers with curves like this one. I don't think it was measured. So it didn't happen in every experiment. Some experiments we have a smooth increase of stress versus time. And then when we have a smooth increase of stress versus time, it goes up to maybe 10 GPa, and then the shock is released. We couldn't maintain it for longer. When the stress goes up and doesn't get extra evolution, so it confirms that what I think is that when we get this peak, this elastic increase of stresses, and then once you have plastic flow, twinning, dislocations, whatever, you relax. So it asks us, what is the strength of iron under high pressure, under shock conditions, under static conditions, and it's kind of a summary figure of the strengths of iron that has been reported. You have the curves from diamond cell experiments here, which are quite low. And then you have this measurement of Ping et al. In 2013 from Livermore, where I want to point out that it's an estimate of stress which is based on temperature measurements. It's not a measurement of stress, it's a measurement of temperature increase, and then it's a model of plastic heating to reinvert the stress. And then our data points, the stress values we measured, which plot closer to what was measured in static experiments. Now, as I said, maybe the peak stress at the onset of plastic flow is higher than what we measure, but a few nanoseconds later, this is where we are. So in terms of plasticity of shock compressed HCP ion, we managed to perform in situ X-ray diffraction measurement of stress of lattice preferred orientation during laser-driven shock compression, and look at those the time dependence of stress and time dependence of microstructures. One limitation is we are shooting X-rays through the whole sample. We're not looking exactly at the shock front. We're looking at the average properties, but still, with observations of a big elastic overshoot prior to the elastic to plastic transition, stress relaxation with plastic flow, which we see in some experiments, which is driven by 1 twins, and it happens in less than a second, less than a nanoseconds when it starts. Conclusions. Yes, as it was said in the introduction, I was supposed to give a talk on March 12, 2020. This is the last email, one of the last emails about it. But then, this happened. Donald Trump closed the border between US and Europe, so I actually escaped from Stanford on March 12, 2020. Just flew back to France, and I didn't expect I'll be locked in for a year after that escape. Lucky I did escape in a way. What I try to show you in this talk is how we use multi-grain X-ray diffraction, and we try to monitor single silicate grains, how they rotate, and what happens when you go through a phase transformation inside a diamond anvil cell. You can also watch grains of HCP metals in polycrystals these times, and how they build stress and texture in deformation experiments, static or dynamic. And then, one side of my work is also to incorporate those into plasticity models to understand the Earth and the evolution of the Earth's mantle and core, for instance, which I didn't speak about today. And with this, I thank you for having listened to me, and I'm ready to take any question. Thank you.
Thank you very much for the talk. So I invite everybody to enter any of your questions in the chat field, and I will read them off for our speaker. And also, please unmute yourself so we can give our speaker a nice round of applause. So there's a question from Jeff Colvin. What role does the geomagnetic field play in this downwelling/upwelling process?
Probably not much. It's more it's a release of heat so the Earth is being heated through radioactive decay, and it's a release of heat.
And Jill Bernier had a question. Did you want to unmute yourself?
Hey, Sebastian.
Hello.
I got a question about your kind of a technical question about the stress analysis from the LCLS data.
Yeah.
Is that are the stresses that you're calculating coming from ISO strain approach, coming from the measured powder diffraction strains?
Kind of, yeah. It's the typical residual stress analysis, that you can do on X-ray diffraction data. There's no complex model of any form.
Oh, like sine squared psi, or the
yeah, sine square, sine square law, yeah.
Okay, that answers my question.
And there's a question from Fnu Saranch. Says the 10 to 12 twinning mode in HCP is extension twin. What it is getting activated, or why do you think it's getting activated during compression?
So it is true that 1O minus 1,2 twinning is an extension twin in HCP ion. It depends on the C over A ratio. But it means it's when we say extension twin, it's extension of the C axis. And as you actually the figure is projected here, as the shock is coming through the sample, the C axis is perpendicular to shock, and it's actually under extension. And so you activate an extension twin.
And there's a question from John Eggert. It says, excellent talk. Can you explain the experimental differences or corrections for when you see the stress drop due to twinning versus when you do not overcome the yield strength barrier and the stress rises smoothly?
So we have, out of the 4 experiments, 4 conditions, we have 2 where we overcame the yield strength barrier and 2 where we did not. And so I can tell you it's not a pressure. One set of experiments at 20 GPa, we did go over it. And the other 2 are in between. So it's not because we were at low pressure versus high pressure. I am not exactly sure. I think it's just the stress in those runs did not reach values that were high enough to activate plastic flow. Now, why did one run reach a high stress and the other one not? I'm not sure.
And there's also a question from Ivan Olyanik.
Mm-hmm.
There's some debate whether HCP phase of iron stable phase at strong shock conditions at pressures of the Earth's core. Is there any signatures of BCC phase in your XRD crushed crystal? And
no, we did not see. Yeah.
And it just also asked how well constrained were the grain positions in strain?
So in the first questions on HCP on iron, we did not see any evidence of BCC iron on the diffraction data. It's HCP everywhere. We see BCC on release, actually sometimes FCC, sometimes BCC, but I don't see any high pressure BCC. It's really, I see HCP. Now, for the question of Chase,
Yes, I apologize. I mixed the second question appeared right as I was reading it. And I got...
So he's talking of multigrain crystallography, and he's asking me for the measurements I had on NaCOF3, how well do I constrain the grain positions and strain? Well, not well, actually. For that experiments, we don't have a good resolution on grain positions. With the new ones, the laser heating experiments, we have actually, when we try to invert with fetal bees the grain positions, it seems very consistent. The strain tensors, I'm not sure. For these experiments with resistive heating, no, we don't get a good position.
Yes. So Chase wanted to speak in first. You can unmute yourself.
Thank you. Hey, Sebastian, how's it going, man?
Good.
Quick, so because when we've done these experiments in the past, I've usually started with a single crystal to minimize the number of what I'm looking at to try and help me expand some of these parameters. So do you think that could be a function of? So you started with, like, I think you told me before, like a very coarse crushed powder.
Yeah.
So you already are starting with do you think that has any effect on that at all? This is something I've been wrestling with myself, because some experiments I have a lot of grains, I find my positions are less constrained. But if I start with a single crystal, they're usually very well constrained, even if I don't use half a scan.
My guess was more experimental, wobble diamond cell.
Okay.
You as you step scan it, especially this experiment on NaCOF3, we were doing resistive heating, so there's a lot of cables going to cell, and I don't, sometimes the rotation is probably not as good as we think. And so I suspect it's more the wobbling. When we do the laser heating experiment, it seems to be much better.
Okay. Yeah, that's consistent with what I've seen too. So I was just curious.
Yeah.
So I had a question. So you have, on this more recent work slide, you were saying you didn't really get to talk about incorporating this into Earth's dynamical models and
Yeah.
predict its properties in evolution. So this is basically like a multi-scale problem that your research is on, studying the microphysical properties of like different grains and phase changes. Could you speak more to how this research impacts like basically the hydrodynamic scale, or how you go up to doing full like Earth simulations?
So usually the way we do it is the global mantle flow or inner core flow. They are very simple model based on fluid dynamics with like a constant viscosity or something like that. And we use the flow from those geodynamics model and we couple it with a viscoplastic self-consistent calculation to calculate the microstructures. So it's not the microstructures that's driving the flow or giving even constraint on viscosity. It's we just put an ad hoc viscosity in this case. People have there are projects here in Lille. Actually, there's a big group who do computations, plasticity computation. They try to go up the scales from dislocation to dislocation dynamics to crystal, polycrystal, to get to mechanical properties. But in my activity, I haven't done it. We go down with a geodynamical model, which is purely the fluid dynamics. We get flow lines, and then we incorporate those flow lines into polycrystal plasticity to get the microstructures.
Thank you. If there are no more questions, let's thank our speaker again.
Well, thank you for having me.